Okay, so we're moving on to chapter 6 of that. So this one we're talking about proton transfer reactions, and then specifically we'll be talking about acids and bases, and as it relates to organic chemistry. It's a little bit different than what you would have learned in general chemistry, stuff like that. So, but we can still apply the same concepts. Okay, so what we're going to initially talk about is the Bronstead-Lowry definition of acids and base. And here we're talking about specifically the movement of hydrogen, so like that. So if you have OH minus, right, classic hydroxide plus HCl, right, this is your classic base, this is your classic acid, so like that. What's actually happening, right, so like that, is that right, so with that coming here, right, this is going to extract the hydrogen from the hydrogen, or from the HCl, to make water and chloride. Okay, so with that, so this is your base, this is your acid. So what we're going to say is that bases, right, so with that, so the base is going to accept a hydrogen, right, and acid has a hydrogen to give away. So with that, so it's always good to think of water is not as H2O but as HOH. It'll make your life a lot easier to think of it that way, plus Cl minus. Okay, so like that. So this is your acid. This is your base. Now, just to mess with you, right? So with that. So remember, this reaction technically is reversible. With that, and so what's going to happen is, so with that. So if it's running this way, if it's running in the forward direction, right, the reaction is going to be this is going to grab a hydrogen, this is going to have a hydrogen to give away. But if we're running in the reverse direction, now this molecule here, right, so here to here, right, so here to here, when in the reverse direction, now this is acting like the acid, right, so this is grabbing the hydrogen, right, so this is acting like a base, but to distinguish it from this base, right, we call it the conjugate base. Right? And here, this has the hydrogen, so and that reaction is acting like an acid, so to distinguish it from the regular acid, we call this the conjugate acid. Okay? Okay, so the base, that molecule is going to be connected to if you're a base on this side, the corresponding product is going to be the conjugate acid. If you're an acid on this side, right, it's going to connect to the conjugate base on the other side. Okay, so bases become conjugate acids, acids become conjugate bases, and I'm assuming that they did the reaction, or did the naming just to mess with undergraduates, so like that. So what we're thinking about here is, if you think about what's going on with this reaction, right? So with that, so we have with HCl, there's a polar covalent bond, right? So you have a partial positive here and a partial negative here. Well, these, the hydroxide, right, it's negatively charged. It's going to be attracted to that hydrogen, right, because it has the positive charge, right? So what it's going to do is it's going to say, okay, I'm going to take one of these one of these pairs of electrons. It doesn't matter which one, and I'm going to transfer it. I'm going to make a bond to this hydrogen. Well, hydrogen only needs one bond, right? So it's got to figure out what to do with these two electrons. So what it does is it pushes those two electrons onto the chloride. The chloride's happy to do it, right? It's electronegative, right? It has its octet filled, and everybody's happy. Okay, so see what's happened, right? So we've taken a lone pair and made a bond to that hydrogen. Then we've taken that so lone pair to bond. And here we've taken this bond, these two bonding electrons, right, and pushed them onto the chloride to make this new set of lone pairs. So you're going to see this a lot: lone pairs to bonds, bonds to lone pairs. Something like that. So you can see that quite a bit. Okay. Now you'll notice here I did what are called curved arrow mechanisms, and what those do is those show where the electron flow. Okay. So with that, and so if as opposed to these, which are straight arrows, okay, these are telling you what reactions are going on. The curved arrows show what the electrons are doing, and so what they do is they usually go to the negative to the positive. Okay, so with that's usually what they're going, because you're showing, because we're moving electrons around, right? So with that, so you can't have, right? So a positive is a lack of electrons. You can have lack of something moving. So what you're doing is you're taking the negative to the positive. Okay, so with that, and so And to show that this bond is being broken, what's happening is those two electrons are being pushed onto the chlorine to make the chloride. So start off with 3 sets of lone pairs, now it has 4. Okay, this one had 3 sets of lone pairs, now it only has 2, because this third set became these two, that bond there. Okay. Now arrows do have there's a lot of symbolism in organic chemistry, and arrows are part of that. Okay, so if you just have a single-headed arrow, that just means a reaction's occurred. Okay, if you have these arrows going in both directions, right? So they can either be single barbed or double barbed. It doesn't really matter. So that means the reaction is in equilibrium, right? So it's going back and forth. Single. But don't get it confused with the double-headed arrow. Okay, so that is showing it between resonance structures, right? We talked about that earlier. Between resonance structures, you're talking about double-headed arrow. That's different than an equilibrium. When we're talking about electron flow, okay, how electrons are moving around, right? We already sort of talked about this with resonance structures, but now we get to move atoms around, right? So these curved arrows are going to show us how those electrons are moving. If it's a double-barbed arrow, it's going to be 2 electrons. If it's a single-barbed arrow, it's going to be a 1 electron moving around. Okay, so like that. So they doing it. So move on a little bit. We're going to talk a little bit about chemical equilibrium and equilibrium constant. We don't have to worry about calculating anything. You did all that in general chemistry. But to just realize that equilibrium, right? The equilibrium constant, right? It's going to be, the concentrations of the products, right, over the reactants. Okay, and don't forget that. What is it? The superscript, the number of moles, molar coefficient out front becomes the power. Okay, let's put that out front here. But again, that doesn't really matter much for this course. Stuff like that. But to just realize that if this number, say KEQ, right, is greater than 1, what that means is we have a large number on top and a small number on the bottom. Okay, since products are on the top, what that means is products are favored. Products, we're going to favor products. Okay, if equilibrium is really small, okay, it's less than 1. What that means is we have a small concentration of products and a large concentration of right. So with that, the concentration brackets, right? So we have a large concentration of reactants, not very much products, right? So that means reactants are favored. Okay. Now, if this is about 1, right? So with that means that we're in none are favored, right? So with that, or I should say they're equally favored, right? So because they have similar concentrations if it's about 1. Okay. Now, so you're obviously not going to have a 0 or a negative, right, equilibrium constant, because you can't have a negative concentration. So it's always up to comparing 1, because it's a ratio. Okay. So let's say if this could be KEQ equal to 1,000. Okay, that would mean products are favored. So for something less than 1, it could be KEQ 0.001. Okay, so here again, there's very little of the products, compared to the reactants. So reactants are favored. Okay, so for here, right, so we're looking at draw the curved arrow mechanism. So one of the things you're going to want to do is usually a good idea to go ahead and put in the, especially when you're just starting out, go ahead and put those lone pairs in. Okay, that's mostly good about that. Okay. You're definitely going to want to put in a formal, if there's any formal terms, those have to be written. The lone pairs, it's usually a good idea to put those in. Okay, so the KEQ, right, is 0.004. Okay, now if you look at this, what's going on is this this molecule here, you compare that to that, right? It is losing the hydrogen. So this is going to be our acid. Okay. This guy here, this is picking up, looking from here to here, right? We've gained that hydrogen there, right? So it wants to grab one. This is going to be our base. So it's going to act no different than hydroxide. Okay, so it's going to be, right, because remember there's a partial positive, partial negative, partial negative, partial positive, right? There's going to be a partial positive on that hydrogen, right? So this is going to be attracted to that. Okay, so this set of lone pairs is going to make a bond to that hydrogen. Okay, hydrogen only needs one bond, so it's got to figure out what to do with these, with those hydrogen or with those electrons, right? So it just pushes those onto the oxygen, okay, to make this extra lone pair here, right? So this set of lone pairs became that bond there. Okay, so not too bad. Okay, the equilibrium constant is less than 1, right? It's a very small number, so that means that reactants are favored. Reactants favored. Okay, not too bad. Okay, so if we look at the equilibrium constant, right, and just relate it to acids, okay, so the typical acid dissociation is just in water, okay, so you have your acid plus water going to your conjugate base plus hydronium ion, H3O plus. Okay. Now in this one here, right, the water, right, so that because it's a liquid, it's considered, you can't change the concentration of a liquid. Okay, so it's assumed to be 1 because there's no change. Okay, same thing as if you have a solid; those are assumed to be 1. Okay, so we can pretty much have that fall out, and so you end up for the Ka equation. Okay, equilibrium constant for an acid and water ends up being this. Okay, products over reactants. Okay, so by that, and so it turns out that the higher the Ka. Okay, right. So the bigger the number, right? So the stronger the acid is, right? The more that it wants to dissociate like this. Okay, so so you're gonna more and more favored, right? The stronger the acid is going to want to push it towards products. Okay, so the bigger the Ka, the stronger the acid. Okay, now, yep. So here we go. So the HCl, the Ka is 10 to the 7th. Okay, but if you compare it to something like methane, okay, it's the Ka is 10 to the minus 48th. Okay, so the difference between these two, okay, so HCl is 10 to the 55th power more acidic than methane. Okay, just to give that number in perspective, atoms in the universe is 10 to the 80th, stuff like that, and so it's it's getting up there, stuff like that, more acidic. Okay? Stuff like that. So, but the problem is, scientists don't necessarily like dealing with these big powers like this. I mean, it's good to know, but it'd be nice to have a shorthand. Okay, and so what they decided to do was to do the pKa. Okay, it's very similar to the pH. Whenever you see the P, that means you've taken the negative log of something. Now you do the negative because then you're working primarily, because most things are actually fairly weak acids that we work with day to day, stuff like that. So then we'd just be dealing with a lot of negative numbers, and people don't like dealing with negative numbers. So they put a negative in front of there in order to be able to make positive numbers. So positive, so really all it is turning scientific notation into integers, or not necessarily integers, into easier numbers to handle, something like that. So, but you have to be careful though, because the negative, okay, you're taking the log. The smaller the number, the stronger the acid. Okay, negative pKa equals strong acids, right? So when you take the negative log of 10 to the 10 to the 7th, you get -7. Okay, so methane becomes, take the negative log of 10 to the minus 48th power, it ends up being 48. Okay, so the pKa difference here is 55. But what that means is the difference again is, because we're talking about logs, So that is actually the difference is 10 to the 55th difference. It's not 55. This isn't, methane isn't 50. Hydrochloric acid isn't just 55 times more than methane. It's 10 to the 55th. Okay, if you're looking at the difference between those two. So bear that in mind. Okay, but again, so just as a reminder, he says, hopefully we learned this before, but if you have a strong acid, okay, so but that, remember we talked about acids, the course, back here, if you had, you've had acid, the corresponding one on the product side is the conjugate acid. You have a base, conjugate acid, acid, conjugate base. If you have a strong acid, like HCl, okay, the corresponding conjugate base, chloride, is really terrible. Okay, it's really weak. So this is a very weak base. Here, water is a relatively weak acid. Okay, stuff like that. So that means its base is pretty strong and stuff like that. So the conjugate base would be pretty strong. That's why hydroxide is a pretty strong base. Okay, so like that. So if you have a strong acid, weak conjugate base. If you have a weak acid, that means the conjugate base is going to be pretty darn strong. Okay, so there's that inverse relationship between that two. So bear that in mind. Okay, so here we go. So we look at the pKa's, right? So that we can tell how strong it is. Okay, so we have methylphenol, right? pKa of 10. This is 10.26. Okay, for chlorophenol, okay. It's, instead of a methyl group here, you just put a chlorine here. The pKa drops to 9.43. Okay, so this is almost 10 times as more acidic, right? Because it's just about 1 pKa unit less. It's a lower number. So that means this one's almost 10 times more acidic. Okay, not just stuff like that. So this has the smaller pKa. That means that's the stronger acid. Okay. Okay, so predicting reactions, okay? So what you want to do is you want to so when you run these reactions, you're going to want to compare the acid on this side, and then you're going to want to compare the acid on this side, the pKa of this, okay, to the conjugate acid on this side, pKa of that, okay? See, the acid to the conjugate acid. What you want is the this number to go up. Okay, so by that, because what's actually happening is you are forming, if you have a low number here and a high number here, that's good. What you're forming is a weak base on here. You want to have the weakest base available as you can. Okay, so by that, so that's actually what you're measuring. You want to have a weak base, because if you produce a strong base, it's just going to rip the reaction. It's just going to rip into the conjugate acid and go backwards. Okay, so by that, so what you want to do is when you look at compare the acid to the conjugate acid, those pKa's, you want that number to go up. Okay, so by that, so if you're looking at here, so you're going from 10.3 to 8.4. Okay, which is favored, products or reactants. So the pKa is dropped. Okay, you want to go towards the higher. You want to have the higher pKa, right? So that means that this is that the reactants are favored. It has the higher number. Okay, so from 6.5 to 13.8. Okay, now the products have the higher pKa, so now the products are favored. Okay, now but don't forget that if you're going from if this is HA, B minus, right? So A minus, HB. Okay, so let's say this is -7 and this is -3. Okay, again, this is going to be the bigger number. Okay, so even though it's 3 compared to 7, it's -7 versus -3. So this would be favored. So be careful when you're dealing with negative numbers, negative pKa's, stuff like that, because again, the number has to go up. So, okay, so now there is the issue of this leveling effect. Okay, and basically what's happening is that no matter what if you have if you're running a solvent that has an acidic hydrogen on it, okay, either so that's one. What's going to happen is your base is if it's if it's stronger than water, right? So let's say you're running water. So if it's stronger than water, it's just going to react with your. It's just going to react with your with the water, and then you're going to kill whatever it is. Okay. So if the acid is stronger than H3O plus, this is what's going to be made. Okay. If it's stronger than OH minus, okay, if your base is stronger than this is going to predominate. Okay, so you're never going to have. So really, this is going to be here. So you have to look at it. Okay, look on these sides, right? So with that, if you dump in here in the presence of this, right? So with that, this is going to. These are going to predominate. So you got to be really careful. So how do you avoid that? So with that, so you have to compare to what you're doing in the solvent. Okay, so because your acids and bases might react with that, and then you're stuck with whatever it is the protonated or deprotonated solvent is. It's actually doing the chemistry. So how do you avoid that? You switch solvents if you can. Okay, switch it so that it can't can't be protonated or deprotonated by your base. You have to be very careful with solvents. So. Okay, so Le Chatelier's principle. So hopefully you remembered this from general chemistry, and this is something that they talk about quite a bit. When you're in a stationary phase, is your stationary state, basically what's happening is there's no product or reactant formation, right? So it's going equally back and forth. It's done where the forward reaction and the reverse reaction are equal. Okay, and so if you have this reaction HB, this should be in equilibrium, H plus B minus. Okay. If you stress the system in a particular, if you stress the system to make it out of balance, what's going to happen is it's going to shift the equilibrium so that the stationary phase is met again. Okay, so if I add product, if I add HB here, so increase this. Okay, so that what's going to happen is so increase HB, right? We're putting a whole bunch of this in, right? So what's going to happen is the equilibrium is going to respond by pushing the reaction that way, okay, towards products. Okay, the same thing is if we remove H plus, right? So if we get rid of all our H plus, the system will realize, oh, criminy, we don't have enough H plus, so it's going to push it this way, right? So you can either add here or remove this. Okay, so like that. So conversely, if we add H plus, okay, so we drop the pH, say we add a whole bunch of this in there, right? It's going to say we have way too much of the stuff on this side, so it's going to drive the reaction back that way. Okay. So wherever the stress is, either adding it or removing it is going to push the system one way or the other. Okay, so one of the tricks that you can do for doing reaction engineering is to say make one of these products to be a gas. Okay, so even if it's a reaction that's sluggish, okay, the gas is always going to boil out or bubble out, right? And then the system will realize, oh no, we don't have any of this stuff left. Let's push it some more. And so you can do this, or you can say add a particular counterion where this is insoluble, and so this will crash out. As soon as this is made, this is crashed out of the system. Okay, so and so what you can do, well, then that'll force the system that way, right? So we're removing. If you remove a product, right, it'll drive the system forward. Now you can do that. You can also add a lot of the HB too. That'll work too. You add a whole bunch of whatever your reactants are. That'll help push that in, push that away. So with that, so you can do either one. If you want to drive the reaction forward, you can either add a whole bunch of reactants or remove a bunch of products, or both. Stuff like that. So that's fine. Okay, so now for thermodynamics, okay, so that now this, before your eyes glaze over, it's only a couple of slides. Okay, it's not that big of a deal. All we're saying is that the Gibbs free energy is simply where energetically where were the products, or where were the reactants, and where energetically are your where does the let me start that again. Where are the reactants? Where energetically, where do they start? And then where did you end with the products? Okay. If that reaction, if the energy goes up or it goes down, okay. If the reactants, going from reactants to products, you've dropped in energy. That's very good. Okay, and so that's considered a spontaneous reaction. Okay, eventually, because the universe wants to get as low of a energy state as possible. Okay, so that's going to happen. Now, if you go up in energy from reactants to products, then it's non-spontaneous. So the easiest way I think about this is your checking account, right? That balance drops spontaneously. I don't know how it happens, but it just spontaneously, by the end of the month, it's dropped almost to zero, right? So like that, but it's a heck of a lot of extra work, right, for that balance to go up. So wherever you started with, it's hard to have an ending balance go up, right? It's non-spontaneous, definitely, but it sure is heck spontaneous going down. So that's easy. That's how I think about it. Okay. Now, don't get confused with spontaneous and kinetics. Those are two separate things. Okay. So your diamond ring that you gave that you either received or you gave, right? So that diamond is in fact thermodynamically unstable. It will turn into a big lump of graphite eventually. It's spontaneously unstable. However, it's going to take 1 billion years to do it. Okay, so it is spontaneous, but that doesn't necessarily mean it's fast. Okay, so two separate issues. Okay, so don't get those confused. Okay, so we can actually plot what's going on. Okay, so with the reaction. Okay, so reaction progress. So it's going this way. Okay, so with that, from where you start. Okay, so we're going to start some arbitrary reactants. Okay. Okay, so with that, and we're going to plot energy. So it's some sort of arbitrary energy. Okay, so with that, and so we're going to say, okay, hey, we want our products, we want this to be spontaneous. So that means our product's going to be in lower energy, right? So this means it's spontaneous because we've dropped in energy. Okay, so this we can measure is what's called delta G, Gibbs free energy, delta G 0. Okay, so with that, but to get there, what we have to do is we have to go through what's called a transition state. Okay, and it's higher energy. Okay, to get the atoms in the proper alignment to do the reaction. Okay, that's going to cost some energy. Okay, and the height of this. Okay, from the tallest peak to where you started to the tallest peak. That's called the activation energy. Activation energy. And that's typically done by delta G double dagger. Now, I have no idea why they do the double dagger, but that's what they do. Okay, so all the delta G's are relative to where you started with the reactants. Okay, your reactants are going to, your activation energy is going to be from the reactants to the highest peak it has to go to get over to the product side. Okay, your your delta G 0, okay, is going to be where the gap between the energy of the reactants to the energy of the products. Now, if it was below it, it would be spontaneous. If it's above it, okay, if it's above where the reactants are, that means it's non-spontaneous. Okay, so there you go. Okay, and then this right there, this highest peak, that's called the transition. The transition state? We'll talk more about that later, but that's the highest part of the energy. It's not something that you can isolate. Okay, you can sort of we have to do quite a bit of work to figure out what that probably looks like, stuff like that. But it's the highest energy species that exists in the reaction. Okay, so with that, and the hump that it has to get over, that's the activation energy. Okay, so functional group and acidities. Okay, so there's going to be a lot of these sort of things, of rules of how acidic things are, because that's going to determine a lot of what the chemistry is going to happen. Okay, it's primarily what drives the acidity. Primarily is going to be the functional group. Okay, so with that, so if you have an alcohol here, right? So if you just have, CH3CH3, right? That pKa, if you were to measure it, is about, I don't know, like 60. Okay, if you measure this, the alcohol, right? So with that, the molecule. So this is ethanol. The pKa is like 16. Okay. Now, if instead you change this and turn that into a carboxylic acid, it's 2 carbons long. You have the OH here, but if you add this double bond O in here, now the pKa is like it's like 5. Okay, so where this what the functional group is going to determine what the pKa of the molecule is going to look like. Okay, if so you need to have a hydrogen on something electronegative. Well, okay, not necessarily. Take that back. So you're going to have a readily available hydrogen. Usually it's going to be on something electronegative. Those are probably going to be the things that are most acidic, stuff like that. But if you have, say, it next to a double bond, okay, or on electronegative group, or having that near it, that's going to drop the pKa of the molecule. Okay, and typically, charged things are going to positively charged things are going to be acidic, while negatively charged things are going to be basic. Not always, but that's a fairly decent rule of thumb. Okay? If you're comparing 2 like molecules, one's positively charged and one's negatively charged, the positively one thing is going to be acidic, the negatively charged one is going to be basic. I'm sure that there's something like that. That's a pretty good rule of thumb. Okay? Now, as far as reactivity goes, I don't have a periodic table, but as you go across the periodic table, so if you look at the periodic table, it goes carbon, nitrogen, oxygen, fluorine. Okay, as you go across here, so if you have the hydrogen on a carbon, as opposed to carbon, a nitrogen hydrogen bond, or an oxygen hydrogen bond, or a fluorine hydrogen bond. Okay, so with that you're going to get more acidic. Okay. Actually, HF is a fairly strong. It's a weak acid, but it's compared to methane, it's really acidic. Okay. So with that, because the electronegativity in this case is going to weaken that bond. However, the farther you go down, it says you're going to also get more acidic on a column. Okay. So here's fluorine, chlorine, bromine, iodine. Okay. So the closer you get with the hydrogen, if the atom is closest to iodine on the periodic table is going to be the most acidic. Okay, so if it's on an oxygen versus a chlorine, okay, if you're going to do water versus hydrochloric acid, right, just from the name, this is going to work. The hydrogen on the chlorine is going to be more acidic. Okay, so you also have, sulfur, phosphorus, like that. So again, so if you compare oxygen to sulfur, an OH bond versus an SH bond is going to be closer to that iodine. It's going to be more acidic. Now, the reason for this is the fact that as you go down the periodic table, the atom itself gets big. Okay, those valence electrons are further and further out. It gets harder and harder to grab a hold of those electrons, right? So they're just not held as tightly. The hydrogen is just not held as tightly, so it's much freer to go. Okay, but if you're looking at where the hydrogen is, the closer that atom is to iodine, the more acidic it's going to be. Okay. Now hybridization also matters too. Okay, so if you have an sp3, it's going to be pretty difficult. It's going to have a pretty high pK. But if that atom is sp hybridized, it's actually going to be pretty acidic. Okay, so acetylene, which is having the carbons at an sp hybridization, the pK is only 25, as opposed to methane, which just has sp3 or any sort of just heptane or whatever. Its pK is going to be like 48. Okay, so this is actually more like 48. Sorry. How about that? So it's going to be, it's going to be almost no acidity to it. Here, not too bad. So that as far as carbon groups go. Okay, having adjacent pi bonds. Now, whether it's carbon-carbon double bonds or carbon-oxygen double bonds or carbon-nitrogen double bonds, doesn't matter. Any sort of pi bond adjacent to where your acidic hydrogen is going to be a good thing. Okay, and the reason for that is that you can get a nice, so acetic acid, right? So with that, so when it gets removed, okay, you're going to make this. Okay, your conjugate base is going to be that. Well, you can make a resonance structure. Okay, and it allows another atom to bear the weight of this negative charge, right? So this is half the time this is going to bear the weight of that negative charge, half the time this oxygen is going to bear the weight. So this can help out this resonance structure. When you have just ethanol, okay, you don't have that ability because you don't have any pi electrons to be able to help out. So that oxygen is going to be bearing the full weight of that negative charge, okay, and so it's much more reluctant to give that hydrogen up. Okay, so that's why this pKa is about 5, because if it loses the hydrogen, it's not a huge deal because we have resonance structures that can take care of it. This one, ethanol, the pKa is about 16, because the oxygen is going to feel, it's going to feel all the pain of that negative charge. Okay, so about that, and so here, right? So if we compare these molecules, right? So CH3, and these effects are additive, right? CH3. Now they're all sp3 hybridized, okay? But notice how these two guys only have one pi bond adjacent to it, but these hydrogens here have two adjacent pi bonds. Okay, so that's going to make it more acidic. Okay, so it's going to make this more acidic because if this gets ripped away, it has more options for resonance structures. You can do a resonance structure on this side or a resonance structure on this side. Here, if we were to rip this away, we'd only have the resonance structure on one side. So like that. So we have more options here, so this is going to be that. So we have these additive effects. Okay. Now you also have these inductive effects. Okay, and so basically what it's saying is, if you have an electronegative atom, the closer it is, the more electronegative it is, and the closer it is, the more acidic the hydrogen is going to be. Okay, so with that, and so because what's happening is that electronegative atom is pulling electron density away, towards it, and so it's weakening, the acidic, that bond. Okay, and stuff like that, and so it's pulling in here. Now, conversely, if you have what are called electron donating groups, so they allow you to put electrons in there, it makes that bond, the acid bond, a little stronger. Okay, so it's going to be more resistant to being ripped away, and so it's going to have a higher pKa. Okay, so with that, so inductive effects. So, right, so with that, so the more electronegative it is, the more electron withdrawing it is. Okay, the more acidic it's going to be. The less electronegative it is, the more donating it's going to be. The less acidity it's going to be. Okay, and charged substituents are going to have a bigger effect than neutral substituents, particularly positively charged things. They're going to have more effect on this. Okay, so they are additive, right? So if you have monofluoroacetic acid, pKa of 2.6, but trifluoroacetic acid has a pKa of 0.3, a negative 0.3. Okay, so the more you get in there, the more it's going to be. And now it's not a one-to-one thing, but it is qualitatively additive. Okay, now they do fall off quickly with distance. Okay, so if you're directly next to the carboxylic acid, right, you're at 2.8, but if you're a little bit farther away, the pKa falls to 4 or rises to 4.0. Right, you're not having as much pull. Okay, stuff like that. So the book goes into this really complicated thing for ranking, stuff like that. But basically, what you need to do is, if you know these issues, okay, you know that you have to have pi bonds next to them. You need to have electronegative groups. Numerous. The more electronegative it is, the closer it is, so things like that. So as long as you recognize those and the fact that they can be cumulative, that's going to be, if you can do this, you can probably do pretty well. Stuff like that. So to get into that sort of level of minutia at this stage probably isn't helpful. So like that. But if you know generally what affects it, you're going to do just fine. Okay. So with just as a reminder for resonance structures, okay, what you're going to want to do is that as you draw these, it's if there's 3 resonance structures, it doesn't necessarily mean that it spends a third of the time in one and a third of the time in the other and a third of the time in the last. Okay, some are more stable than others. Okay, so the biggest, the most likely it's going to be is the one that's the most stable. Okay, so it may only spend, the first and third each of those may only spend 10 times, and the rest of it is the second one. Maybe the majority of the time it's in that the molecule looks like that resonance structure. Okay, so what you want to do is you want to make sure that you look at, when you're looking at the resonance structures, do all the atoms have a complete octet? Okay, are there the most amount of covalent bonds? Okay, can you minimize the number of atoms that have charges to them? Okay, so that's formal charges. Okay, and stuff like that. So, but the other thing you can look at is to say, if you do have a charge, okay, where is it at? Okay, so the most electronegative, right, atoms, they're going to want a negative charge. Okay, and so if you can put a negative charge on an oxygen versus a carbon, right, oxygen's going to be more electronegative. Okay, and so that's where it's going to be. That's where it's going to want to be. So in this one, the negative charge is on oxygen. Here, the negative charge in this structure, the negative charge is on carbon. Okay, so like that. So you want the negative charge to be on the oxygen. Now, conversely, if you have a positive charge, okay, you want that to be on the least negative. So if we were bouncing around a positive charge in this resonance structure, where you'd want that to go is you want that to go on the carbon, because it's less electronegative than oxygen, right? Because it's farther away from fluorine, so by the periodic table, right? So there you would want it to be on the positive. Okay. The other thing to look at is what are called the primary, secondary, and tertiary. So all we're doing is we're saying how many other carbons, right? So for that, so if you have say, you have your 4 bonds, okay? So if you have one carbon group in here and the rest of these fluorine, right? So you count how many things are hanging off of that carbon, right? In this case, it's just 1. Okay, so we call that a primary. Okay, 1 dot. If we have here, right? They're always going to have 4 bonds, right? And they're almost always going to have 4 might have 4 things hanging. But we're asking how many how many carbons are hanging off of that particular carbon, right? So here it's 2, so this would be a secondary, right? If you sort of see the trend here. If you have 3 carbons and a hydrogen, right? So 1, 2, 3, right? So this would be tertiary, right? And here, let me just here so you can see it. C, 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 right? So this one here, right, you've got 4 carbons hanging off of it. Okay, so this is considered a quaternary. Okay, now, when you have resonance structures, okay, if you want to, particularly for positive charges, right, this is going to be more stable. Okay, so if you have the option to have a positive charge on a primary versus a positive charge on a tertiary carbon, you're going to want to put that positive charge on that tertiary carbon. Okay, so like that. So and down here, right? So if you have, okay, so you have this, right, versus that. Okay, so here, right, you've put in your dots for your carbons, right? So how many dots are hanging off of that carbon? Well, there's 1, right? So this is a primary. Okay, put in your dots here. How many dots are hanging off of that carbon? Well, there's 2, right? 1, 2. So this is secondary. This is going to be a lot more stable than this primary one. So this is going to be the more. This is where it's going to want to spend most of its time. Okay, so like that. It wants it to be having those the positive charges on here, right? So okay, so with that, so you have to be careful of where it is. It's not just that there's positive charges are moving around, but this is going to be a bigger contributor to the resonance structure. Okay, good luck.